Alright, so let us next prove this result. Length is finitely additive. We have already seen the statement, we saw it in the previous analysis video, but let us see it once more before proving. Here I is a bounded interval and P is a partition of I of cardinality n. Of course, by definition P is a finite set. So P will have a cardinality n where n is some natural number. Then we have to prove that the length of I is equal to the sum of the lengths of the subintervals which are elements of P. And we are now going to prove this by induction on n. So let's start the proof. We apply induction on n. So the least value of n will be 0 when n is 0. What is P? Because P is P has cardinality n. So P in this case will be the empty set. But if the empty set is a partition of some interval, what can we say about that interval? The interval itself should also be empty. In this case, I itself is empty. However, exactly how are we getting this? Let us recall, because we are going to talk about partitions a lot, let us recall the actual definition of a partition. What does it mean for P to be a partition of I? The definition is that P needs to first of all be a finite set, and the elements in P should be bounded intervals themselves. Each j in P should be a bounded interval just like I, and each j has to be contained in I as a subset. But this is only one part of the, all the conditions. Additionally, every element of I needs to belong to exactly one j in P. In other words, for any chosen x in I, there should exist exactly one j in P such that x belongs to j. This last condition is equivalent to the statement that the distinct elements in P are disjoint. In other words, the elements in P are mutually disjoint. If we take two elements in P that are distinct, then they have to be disjoint. They should have empty intersection, and I should equal the union of the elements of P. Now, when you think of this case where P itself is empty, then this union becomes the empty union, and by definition of union, the empty union is nothing but the empty set. So that's how in this specific case I itself is the empty set. But then on one hand, I being empty has length 0. On the other hand, what happens to this sum? This sum is nothing but the empty sum, and by properties of sums over finite sets, this empty sum is equal to 0. This is one of the properties do you remember in chapter 8 where in the very first section we discussed sums over finite sets, and there itself the very first part proves this. So it's coming from there. In other words, when n is 0, our claim is true. Actually, right after this we can assume our induction hypothesis, but the author has decided to see one more case, namely when n is 1. So let us next see that. That is also trivial, just like this one. When n is 1, then P has exactly one element. Let that single element be J. Again, we can use this fact. This is not a part of the proof. This is our extra. We are simply writing all these things down so that we can better understand the proof. After this, we have this. Now, if you, in place of the empty set case, if you take the singleton set consisting of J, say, then again by another, we are not talking about sum, this is union, right? So this union of course will be simply J. So in this case, I becomes equal to J. In this case, I is equal to J, and the length of I of course then is nothing but the length of J, but that is just this. If this looks a little strange, you can also denote the general interval by say J prime. Okay, and this is one of the other properties, maybe the second property of sums over finite sets. Here itself I was going to talk about that, I got confused because this is not sum, this is union. So in this case also we see that in a very simple manner our claim is still true. So now we can assume our induction hypothesis. So we should not perhaps write so, because we are going to make a hypothesis, an assumption. Now assume that the claim means what we are trying to prove here, that equation is true for some integer n greater than or equal to 1. What it specifically what it means in detail is that if I is a bounded interval and P is a partition of I of cardinality n, then this equation is true. The length of I is equal to the sum of the lengths of the elements in P. Now let I be a bounded interval and P be a partition of I, but this time of cardinality n plus 1. n plus 1. Okay. Now note that n has the least value 1, I mean n can be 1, okay, or n can be some higher number. We don't really know, here n is something fixed but arbitrary. Because n can be 1, so the smallest possible value of n plus 1 now is 2, alright. So depending on what our interval I is, we have to see how P can actually be a partition of I. In other words, what I am saying is that first of all, of course, all we have to do is we have to see what I can possibly be. So in the beginning itself, we will try to dispose of the simplest cases. Now, can I be empty now? No, I cannot be empty. Keep in mind that this is also an interval. It's a degenerate interval. Why can I not be empty? That's because our partition P now has at least 2 elements. Okay. If I is empty, then there are only 2 possibilities for our P. One of them is this, and the other is this. Why? That's because again the sum of the union of the elements of P has to be equal to I. So if that union has to be equal to the empty set, then either the union itself should be empty or the only set involved in the union should be the empty set. And these are the 2 cases. However, in this case, the cardinality is zero, and in that case, the cardinality is 1. But now we have already seen that the cardinality is at least 2. So that means I cannot be empty. I has to be non-empty. We will, however, not write all these things. We will simply write since n plus 1 is greater than or equal to 2, we cannot have this. That means this case does not even arise. If, however, I is non-empty but still degenerate, okay, I mean, it's not necessary for I to be empty to be degenerate. There is another case in which I can be degenerate. Namely, I can be a singleton set like this. For some real number A. In this case, what can P possibly be? Let us see. Okay. Before writing anything, let's see here. So now our I has exactly 1 point. Because the elements of P, when you take their union, should be equal to I. So at least one element of P has to be non-empty, and that in fact also is the case because this single element A from I has to belong to some J in P. Now by the definition of partition, so there should be at least one element J in P such that A belongs to J. This J, however, at the same time should be contained in I. So the only possibility now is that j is equal to I. Alright, j is equal to I. But of course, our P has at least two elements. So what else can you possibly bring as an element in P besides j? Keep in mind that that element, whatever else you bring in P as a possible other element in P other than j, first of all, that element should also be a subset of I, and that should be disjoint with j, because these are the conditions that P has to satisfy. So the only possibility is that besides having j in P, which is actually nothing but I, you can have the empty set. Because once you have taken I itself, everything in I has already been covered. So nothing else is left for any non-empty interval to be also included in P. That's why anything else you want to include in P, it has to be the empty interval and nothing else. Because you cannot bring one more interval, say, that will be disjoint with all these things. And that is also different from both I and empty set. So this is our P now. So that's why we write then P is equal to this. And in this case, we have hit the minimum possible number of elements in P, which is 2. And in this case, let us see what is the status of our conclusion. First of all, we take the, well, if we start like this, we can still do, okay. We start with the length of I. This we can write as this, because the length of the empty set, that interval is 0. And this this term is nothing but this. Or which is now our P. The sum now is over P. That means in this case also our claim is true. So both the possible degenerate situations, in one of them I is empty and in the other I is a single point. In both of these cases, our claim is true. So we can now move on to the non-degenerate I's. Okay, non-degenerate intervals which have non-zero length. These are intervals having 0 length. So we can now assume that I has one of these 4 forms. I is either a closed interval or a half open interval of the closed open type, or a half open interval of the open closed type, or an open interval for some real numbers a and b such that a is less than b. This condition ensures that none of these intervals is degenerate. Now cases will arise depending on whether B belongs to I or does not belong to I. We will first consider the case where the point B is in I, and that is possible in two of these four possibilities. This one has B and this one has B. Now let B belong to I. Then I is of the form this or this. Whatever the case may be, which one of these I actually is, this element B of I has to belong to some subinterval from P by the definition of P, since B belongs to I, there exists some element K in our partition such that B belongs to K. Okay. Now watch the situation carefully. Our let me draw a small diagram. This is our interval, right? And say this is A, the point A, and this is the point B. And this is our I. The left endpoint A may or may not be in I depending on the situation. We are not saying anything specifically right now itself. But B belongs to I, and that's why there exists an interval K in P, an element of P that contains B. Now note the other restrictions on K. K itself should be a bounded interval and K has to be a subset of I. That is why K itself must be of one of these three forms, two of which are related. Let me write, the reason, let me write the reason itself. Since K is a bounded interval, this is not how it's written in the text. Of course, because the text has to, there is no need to write everything in detail. It's up to us how much we want to write, how much we want to skip. Since K is a bounded interval and K is a subset of I, K is of one of these forms. Closed interval C comma B, open closed interval C comma B, and singleton set B for some C satisfying these inequalities. The case is in fact a special case of this when C is equal to B. I mean, that possibility is there, no? C can be B. So in that case, if K is this, then it just reduces to this. So there is a left endpoint C. This C may be A, may not be A, it may be greater than A, it may be equal to A, we don't really know. So C lies in between A and B, and that too, K may itself contain C or not contain C. And this special case also is possible where K just has the single point B itself. Keep in mind, K can be degenerate because this is also an interval. As an element in P, K can be degenerate. There is nothing wrong with that. I, however, now is not degenerate. Okay, so that is our assumption. Alright, now depending on the various cases that are now possible, we are going to go through a lot of reasonings. All these reasonings, of course, none of them appears in the text for restriction of space. I mean, you cannot just write everything down one after another. We will do it here. Now the thing is that this is our I, right? Oh, I wrote K here, sorry. This is our I and this is K. So without being too specific or too rigorous, that much is K, the entire thing is I. So this should be I difference K. And just from the figure itself, you can see that the length of I difference K and the length of K, if we add them up, we should get the length of I. In fact, that is going to be our next claim. And the author has simply written this: in any case, whatever the case may be, whether I is this or this, and then in each case whether K is this or this or this, in any case we are going to have this. The length of I is equal to the length of I difference K plus the length of K. This, however, immediately raises one question. How do we know that I difference K itself is an interval and not some other set? Well, we will now see how this is the case. I difference K will be an interval and the lengths will be related like this. Let us now go through the cases. Let me first take this case. Under this case, these are the three possibilities for K. Let me number them, that way they will be easy to recognize. Let me first take this. In this case, what is going to be I difference K? From I, we are removing all the points in K. So you can see that it will be the closed open interval A comma C. If you still want to go into the details of even this, that however I won't do here, you try to actually show that this set is equal to this by showing that this is a subset of this and this is a subset of this. In fact, I think you should do it. Okay. In the second subcase, I is still this, but K now is this. If we remove this k from I, then I difference k will be closed interval a comma c, because this time we are removing the right hand side of c, not c itself from I, because c is not an element of k in this third case. And then there is this third one also. Actually, there is no need to verify this third one separately, because it's a special case of this, no. But anyway, because it's there in the text, so let us do this also. In this case, k is just the point B, so we are simply removing the point B from our thing. And that is why I difference k in this case is this. However, keeping in mind that this is just the case where B is equal to C, so we get this. We will need all these cases, okay, so we will keep this calculation. But this is only when I is the closed interval a comma b. Let us next consider the case where I is the open closed interval a comma b. In this case, also k can be the closed interval c comma b. In this case, I difference k will be the open interval a comma c. However, if k is this half open interval, then I difference k will be the open closed interval a comma c, arguing like this case. And finally, if k is this, then I difference k is going to be the open interval a comma b, and that is nothing but the open interval a comma c. Alright, now you just look at the situations. Of course, we have many cases, but in every case, the left endpoint of I is A and its right endpoint is B. The left endpoint of K is C. Here the left and right endpoint are actually the same in this third case, and the right endpoint is B. And the left endpoint of I difference K is A and its right endpoint is C. See, left endpoint is A, right endpoint is C. Left one is A, right one is C. A, C, A, C, A, C. And that is why no matter what the case is, the length of I is B minus A. The length of K is B minus C, and the length of I difference K is C minus A. Now if we add them up, add these two things, then we are going to get B minus C plus C minus A. This is B minus A, that is the length of I, and that's what we were claiming. In any case, we have this. Oh, actually, I think I forgot to write something, namely the form of the intervals that I minus K is. It's there in the text. I mean, the text writes that in any case, I difference K is one of these four intervals. closed interval a comma c, closed open interval a comma c, open closed interval a comma c, and open interval a comma c. Let me not write that again here. Okay, so this is the thing. So this is one claim that we have verified right now, but there is one more claim that the author next makes, and that claim is that now there is no doubt about the fact that I difference k is also an interval in all these cases, because we can see that, okay, whose left endpoint is a and right endpoint is c, regardless of the type of the interval. Now the next claim is that from the original partition P, if one removes the element k, then the resulting set becomes a partition of I minus k, I mean I difference k. Next, let us verify this. Okay. Also, P difference k is a partition of I difference k. For this, however, we need not look at all these cases separately. This we will do theoretically, and again, not as a part of the proof, but as a rough work. Let us see how. These things we do not need anymore, so we can wrap them up. So now our claim is that I difference k is a partition of, P difference k is a partition of I difference k. What are the things that we need to see? We have to see everything, okay. First of all, P difference k is finite, since it is after all a subset of P, and P is finite because P itself is a partition. Also, any element in is a bounded interval. Why? Because if this J is after all in P, and every element in P is a bounded interval, so it's also a bounded interval, and J is a subset of I. All these things we are able to conclude just from the fact that P is a partition of I. However, this is not enough. We want J to be a subset of I difference K actually. Note that since J belongs to this, J is different from K. Since J and K both belong to P and J is not equal to K, so using the fact that P is a partition and so distinct elements are disjoint, we have this. So J is a subset of I and J does not touch K. Hence, J has to be a subset of I difference K. So that way, every element in this collection of sets is a bounded interval and is a subset of I difference K. Moreover, this is a finite collection of sets. Next, we have to prove that every element of I difference K belongs to exactly one J from here. So let X be any element in I difference K. Alright. Since X is after all an element of I, there exists a J belonging to P such that, because P is a partition of I, X belongs to J. Alright. However, we want this J to be in P difference K. Okay. Since X does not belong to K, because from this we can see that X is not an element of K, J cannot possibly be equal to K because X is already in J and X is not in K. Hence, J actually belongs to this. But still we are not done, because next we have to show that J is the only element in P difference K to contain this X, namely that it is unique. Suppose not. Suppose there exists J prime in P difference K such that J prime is not equal to J, but still J prime contains the element X. Then something will go wrong. What is it? Since J and J prime, you see, J and J prime are both elements of P difference K, means after all they are elements of P, and X belongs to both of them. So X belongs to their intersection. That means these are not disjoint. But then, as elements of P, if they are not disjoint, they have to be identical. This forces J to be equal to J prime, contradicting that actually they are not the same. That is why our supposition is wrong. That is, there is no other J prime in P difference K which will also contain X. And this proves that our J actually is unique. And that's why this claim is true. Alright. Now, having seen how this claim is true, next we are going to take advantage of this whole situation. Now, here's the thing. I difference K is a bounded interval P difference K is a partition of I difference K, and there is something else also. The cardinality of P difference K, because P has cardinality n plus 1, removing one element will give us a set of cardinality 1 less than that, that is n. That means we can apply our induction hypothesis on this interval and this partition. So, by the induction hypothesis, the length of this interval should be equal to the sum of the lengths in this partition of the interval. Now we use this, we substitute this expression in that equation where we have the length of I is equal to the sum of the lengths of I difference k and k. Hence, let me start like this. In place of this, we can write summation length of j as j varies over p difference k, and that single length can also be written as summation j, where j belongs to the singleton set k. And in writing this in place of this, we have again used one of the properties of sums over finite sets. If you recall those properties, another property of that result says that when we have a sum like this, where the sets involved are disjoint, this is disjoint with this. This set has intervals, none of which is k, and this has only k. In that case, you can write the sum of those two sums as a single sum. Where the j runs over their union. Because I am writing so many things, so why not I write like this also. And that is nothing but this. So we wanted to prove this, right? And we have it. Unfortunately, this is not where everything stops, because do not forget that we are still under a condition only, namely that the point B belongs to I. The right endpoint of our I is in I, but that may not be the case. On the other hand, if B does not belong to I, then I is of the form closed open A comma B, or of the form open A comma B. Now in the previous case where B belongs to I, you were able to use the fact that P is a partition of B to find an interval K which contains that right endpoint B. Here, however, you cannot do that because the right endpoint actually is not an element of I. Instead, you write like this. In this case, there exists an interval K in, why am I writing like this? K in P of the form C comma B or open C comma B. Okay, one of these two forms where we have this. Well, actually you can take C to be less than P. Yeah, there is no need to consider the case C equal to B. However, this is just simply out of the blue we are claiming something, and it's not done if we don't do anything about it. We have to prove it. Simply saying something is not true. I mean, well, it is true, but we haven't shown that it is true. And this is one of the exercises, and this is exercise 3. So, when solving the exercises, we will see how this is true. And then, using this K, one can proceed exactly similarly as we proceeded with the other case. So, let me just simply write the rest of the proof is similar with this K and such I. Keep in mind that when I write something is similar, rest assured that I have actually myself gone through the entire thing. So you also please do that. Don't just keep it hanging like this here. So in this case, what you have to do, you have to again go through all those steps. You consider both the cases that I may be this, I may be this, also K may be this and this. And then what? Then same thing. This will continue to be true, and also in this case also you can prove that this is a partition of I difference K, and then the rest is exactly the same. Only this much you have to prove. So with that, our proof is over, conditionally over, provided that you do these things. Now, after proving this very important result that length is finitely additive, there is one more thing that we will need, namely finer partition and coarser partition. So next let's see that. It's a definition. Finer and coarser partitions. There is something similar in topology, finer and coarser topology. Finer means, say you have a bag full of stones. You hit the stones with hammer, they break down into smaller parts. So then you say that the stones have now become finer. The more you hit, the more things break, the finer it will be, until you get really powdery particles. So the situation is somewhat similar here. Finer and coarser means it's more grainy, okay, that the individual stones are big. So this is the thing. Let I be a bounded interval. Let P and P prime be partitions of I, two partitions of the same interval. We say that P prime is finer than P if for every interval j in P prime there exists an interval k in P which contains j as a subset. So it's like the coarser partition P prime has large stones, large intervals k. You have broken them down into smaller stones which used to be parts of some larger stone. So this j is a smaller stone and this k is a larger stone from which it has broken apart. In that way you can view this the justification of this finer and coarser. In other words, a finer partition is a partition whose elements are parts of another partition, something like this. So this is your I, and say these subsets are the subintervals which form P. Okay, so that is the original partition, and these are the Ks, so K1, K2, K3, etc. Another partition which you get by breaking down these partitions is P prime, and the elements of P prime are inside some element of P, J3. Say breaking down this element of P into say 3 parts, you have got 3 elements of P prime. So that's why for each J in P prime there should be a K in P which contains that as a subpart. So in that way P prime is finer than P. When P prime is finer than P, we also say that P is coarser than P prime. I need a little ink. Whether as human beings we take multiple births or this is the only life that we have, I don't really know. But one life really is not enough for mathematics. Even multiple lives would not be enough for mathematics. Okay, so in that same case, we also say that P is coarser than P prime. P is less refined than P prime. And then an example to illustrate this. consider the two partitions of the bounded interval 1 comma 4. Let me give them names also. Let me call it P1. So P1 consists of these subintervals closed open 1 comma 2, then the singleton set 2, then open interval 2 comma 3 and closed interval 3 comma 4, and another one P2 which has just these two sets. One can easily see that both of them are partitions of this interval. P1 is finer than P2. Let's verify. Is every element in P1 inside some element in P2 as a subset? Yes. This is a subset of this. This is also a subset of this. This is a subset of this, and this is also a subset of this. And both P1 and P2 are finer than the partition which has only one element, namely the interval itself. And this is the coarsest possible partition. Why? Well, just the fact that P1 and P2 are partitions of 1 comma 4 immediately tell us that all these elements are subsets of this, because that's a part of the definition of being a partition. And there cannot be any partition coarser than this, because you can understand why. I mean, you need to have at least this in your partition. This is the biggest stone that you can have. I mean, you have the entire thing and you haven't even broken down the thing into pieces. That also, in a sense, is a partition. Note that there is no finest partition of 1 comma 4. Why? In fact, the author asks why. That's because, and he offers an explanation, well, a hint. He says that, note that every partition is a finite set. Say you consider a partition, some arbitrary partition, say like this, of 1 comma 4. Note that since the union of these ji's has to be equal to 1 comma 4, so at least one ji itself should be a non-degenerate interval. In other words, we cannot have each ji either empty set or singleton set, because if that is the case, then the union of all the ji's would be a finite set. However, this is an infinite set. This is a finite union of finite, a finite union of finite sets. That's why it would be finite. if all the ji's are degenerate. But this is infinite, and so at least one ji has to be non-degenerate. Without losing generality, say J1 is non-degenerate. Non-degenerate means having some length. You can then break that down into two subintervals, giving you another partition in place of P, which is finer than P. In that new partition also, you can continue breaking down things without any end. That's why there is no finest partition, although there is a coarsest partition. And the fact that there is no finest partition, in fact, is what makes our things possible. Later on, when we are going to use partitions to define, to do many things, one of them is define upper and lower Riemann sums. So the fact that there is no finest partition will help us. Oh, and one more thing, we never compare partitions of two different intervals. Compare partitions of different intervals. For example, if P is a partition of the interval say 2, 5 and P prime is a partition of 1, 4, then we don't say that P prime is finer or coarser than P. This relation of being finer or coarser is only for partitions of a single interval. You can understand why that is the case. If you try to compare partitions of different intervals, the condition for being finer, it's like taking 2 bags of gravel stones and then asking which one is finer, which one is coarser. It doesn't really make sense. You can say in the actual situation of gravel stones, you can say that, say the stones in one bag are finer, but not in this sense. This is only an analogy, right? And finally, there is one more thing before this section ends, which is the notion of common refinement. And this is definition 11.1.16. Let I be a bounded interval. Let P and P prime be partitions of I. The common refinement of P and P prime denoted like this: P hash P prime is defined as this. So what you do, you take all the elements of P and all the elements of P prime and take intersections of them in all possible ways. This is what we mean by that. P hash P prime is the collection of all such intersections where J is coming from P and K is coming from P prime. I think the author has taken K from P and J from P prime. It does not matter. You can use any letters here. So you take all such intersections and their collection is going to be called the common refinement of P and P prime. And a simple example to illustrate this. Consider the following partitions of the closed interval 1, 4. One of them is P, which consists of this closed open interval 1, 3 and then the closed interval 3, 4, and the other is P prime consisting of the closed interval 1, 2 and open closed interval 2, 4. Then P hash P prime, well, you take all possible intersections, okay. The intersection of this one and this one is this one itself because this is a subset of this. So one of the elements is this. The intersection of this one and this one is the open interval 2, 3. If you find it somewhat difficult to see why it should be like this, you draw the figure. Okay, on the real line you plot these points and then you see what intervals you are getting and what their intersections should be. Then the intersection of this one and this one is empty because these are disjoint. And finally, the intersection of this one and this one is this itself because this is a subset of this. And now the section ends with this next result, whose proof is one exercise. Of course, this notion of common refinement hasn't been just defined out of the blue with no apparent purpose. The fact about common refinement of two partitions is that it also becomes a partition of the original interval and is finer than both the individual partitions. The next lemma says that. Let I be a bounded interval and P and P prime be partitions of I. And oh, one more thing. Just like we do not compare partitions of different intervals, we also do not take the common refinement of partitions of different intervals. They should be partitions of the same interval. Then is a partition of I that is finer than both P and P prime. For this, C exercise, I think it's 4, yes. Okay, so with that, our first section of integration is over. After this, there are some exercises that we will solve next Sunday. So that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.